Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We have been discussing about this interception of suspended solids, and we are trying to, in the last lecture, at the end of last lecture, we started discussing about the reason why these fines get migrated in a porous medium. That means, a part of the porous medium itself, which was attached to the wall, and now that is getting dislodged from the inner wall, and it is traveling downstream, and essentially that is being intercepted at the downstream. So, we have been talking about fines migration in this lecture. So, we discussed this potential as a function of z, and we said that this is the concentration profile one will end up for positive and negative ions, and we said that at infinity the concentration of this plus and minus, they have to be C0. That means, we had drawn this concentration profile as a function of z, and we said this is C0, and plus and minus, they are converging to C0 value. This is z, this is C, this is C plus, and this is C minus, and this value is C0. So, this is something which we have already discussed. Now, if we take this Poisson's equation, replace this rho EL by this quantity, okay, and try to solve this. So, one ends up, I mean, I am skipping few steps, I am just trying to give you the final result here, because this is it will be e to C1 e to the power mx, there will be this term, and then one can write this in terms of sine hyperbolic this quantity. Okay. So, if we solve this, because we have the z is C plus z minus C minus z, and the C plus will have e to the power something, minus C minus will have e to the power something. So, e to the power x minus e to the power minus x. So, that kind of relation will end up with sine hyperbolic expression for sine hyperbolic. So, this is what we have for grad square phi, which is writing it as d square phi dz square. And then sine hyperbolic, this quantity, we can replace it by this quantity itself, that is sine hyperbolic u can be replaced by u, provided this is small, and this is small means this quantity z e zeta. What is zeta now? We said that potential would come down like this, right, with z. So, and this is the potential which is coming down. The potential at the wall, this is known as zeta potential. This is defined as zeta potential, and there are ways to measure this zeta potential. So, this is referred as zeta potential. Now, instead of phi z, we can see that the phi would always be less than zeta value, zeta potential. So, instead of phi, we replace this z d zeta, and as long as this z d zeta, the numerator is much less than k b t, then one can replace this sin h u as u. Okay, that is what has been done in this step with this approximation sign, and one can show that for standard parameters, for example, z is considered 1 or 2, E is the charge of an electron, T is, if you take ordinary room temperature, Kb value is, that is a Boltzmann constant available. If you put those numbers, one can get zeta as much less than 26 millivolt at room temperature. So, if someone is working with a system where zeta potential value is much less than 26 millivolt at room temperature, so one can say that this approximation is valid. So, then this approximation is now it is written as phi z divided by lambda d square, where lambda d square takes into account this entire term. This is called lambda d square. So, phi z by lambda d square. Now, lambda d, if you look at it, this if phi changes like this, okay, so then one can write phi is equal to, if you solve this equation d square phi dz square phi z by lambda d square, if one solves this with this assumption that at z is equal to 0, with this boundary condition that at z equal to 0 phi is equal to zeta, and at z equal to infinity phi is equal to 0, because it is tending to 0. If one uses this boundary condition and this d square phi dz square is equal to phi z by lambda d square, then one can get phi is equal to zeta e to the power minus z by lambda d. So, that is the form one can end up with, and then one can say that lambda d is some characteristic length, okay, some characteristic length by which this potential value comes down to some to a significant extent. And what is that significant extent? That you can find out from here. So, this lambda d is referred as d by length, and this lambda d is one measure of the thickness of this electric double layer. So, now lambda d is this. So, this is one way one can do it, but we are not exactly. So, now this is the zeta potential, and this is how we have defined it here. We are not exactly interested in a one dimensional problem like this. Rather, if we work with a parallel plate geometry, not like it is z tending to infinity, if we work with a xz system where x is in this direction and z is at the center of a channel, and channel is comprising of two parallel plates. The distance between two parallel plates is h. So, if this is the case, distance between two parallel plates is h and z starts from the center. So, z goes from minus h by 2 to plus h by 2. If that is the configuration, and then one has to solve this equation d square phi dz square equal to phi z by lambda d square, but now with a different boundary condition, not this boundary condition. Now, if you work with this boundary condition of parallel plate geometry, where phi plus minus h by 2 equal to 0, phi at plus h by 2 is equal to 0 at the wall. Sorry, this has to be zeta. Phi plus minus h by 2 has to be equal to zeta. That means, at z equal to plus h by 2 phi would be zeta, z equal to minus h by 2 phi will be zeta, and due to symmetry at the center at z equal to 0. So, at z equal to 0 d phi dz has to be equal to 0. So, this is something which is, these are the boundary conditions now applicable if you are looking at a channel, because gradually we are heading towards porous media, because we are not interested in a infinite medium. So, now if one solves this equation, this would be the C 1 e to the power z lambda, because this is a general solution here. Solution of this equation is C 1 e to the power m x plus C 2 e to the power minus m x. So, that same equation we are solving here also. Here also we solve the same equation, but in this case, since at z equal to infinity phi tends to 0 and z equal to infinity, this term was going to infinity. So, at that time we set C 1 as equal to 0, and so automatically at z equal to 0 we used this other boundary condition, at z equal to 0 phi is equal to zeta. So, from there we got this zeta is equal to C 2 into e to the power minus 0. So, C 2, so that is why the C 2 was replaced by zeta at that time, but now we have a different boundary condition. So, we have to follow. So, this is the governing equation, this remains same, but then you have to put these as the boundary condition, and you have to find out what is C 1 and C 2. For example, one condition will be C 1 by lambda d minus C 2 by lambda d equal to 0. So, you have to work with these boundary conditions. If one does these, then one gets a solution out of it, which is phi z is equal to zeta cos hyperbolic z by lambda d divided by cos hyperbolic h by 2 divided by lambda d. So, this is the equation for phi z. So, one can see that this phi z would be one can see that it would be zeta at the wall, and then it will change to 0 within a very short distance. I mean, if we look at it this way, here also we will have a dy length on this side, here also we will have a dy length, that though this would be much smaller. I mean, here I am drawing it much larger. If this h is 1 micrometer, this is much smaller to that effect. So, now here it would be from zeta to this will come down to 0. So, from zeta to it will come down to 0, and then it will remain 0, again it will go to zeta near the wall. So, that is how we are looking at the profile for phi in this case inside a channel, and that profile is given by this equation. Okay. If you plot this equation, you will get this kind of a plot, that this would be the phi is equal to 0 most of the places, and near the wall it would go increase to zeta, and here it will increase to zeta. So, this would be the type of profile one can get, and this is exactly that is what you get here. Now, with this phi z being known, a situation where we have this wall all positive charges, it has now it is positive charges here, and we cooled in, let us say, negative charges. I mean, it is not a deprotonation. Deprotonation would have taken give SiOH, and we said that deprotonation leaving SiO minus, but it is not, it is some other, it is made of some other material, and some other charge transfer has taken place. So, let us say now this is the situation here, you have all minus charges, they are tucked here. Now, suppose I apply a voltage across these in this direction. So, if one applies a voltage, this is positive and this is negative, you can see the symbol here. If one applies the voltage there, you can see that what they have done here is that this here the potential that is applied at this point is delta V against the potential on this end is 0. So, that means delta V is the potential that is applied across this, and pressure on this side is 0, pressure on this side is 0. So, there is no pressure gradient, only there is a voltage gradient. So, because of this, what this will do is, since these are negative charge and these are positive charge, this is the plus electrode, positive electrode. So, these negative charges, there would be more free negative charges here. So, these negative charges would be pulled towards this positive electrode. So, because these negative charges are pulled towards the positive electrode, so they will impart a body force on the fluid, the neutral fluid that is inside. So, they will impart a body force on this neutral fluid, and so one can see there is fluid continuously flowing from left to right, and this type of flow is given the name electro-osmotic flow. So, one needs to solve the Navier-Stokes equation to find out, okay, what would be the velocity profile, etc. So, one needs to solve Navier-Stokes equation, which is written here. This is the transient term, this is the convective acceleration, this is the grad of P external, which is 0 anyway in this problem. Then you have that viscous terms here, and there is one additional term which was not considered earlier. This is minus rho El grad of phi external, and this is the Coulombic. You remember what was the Coulombic? Suppose I have in an electric field, if there is a charge q is placed, so by what force it would be pulled, that is known as Coulombic force, right. So, E is basically minus grad of phi external, right. So, E is grad of the potential, electric field is grad of the potential, and there is this q is the charge. Okay. So, it is synonymous term is charge density here. So, because these terms in Navier-Stokes equation, they are on a per unit volume basis. So, one needs to consider these, and these would be the body force term one has to consider in Navier-Stokes equation. So, by considering these additional term and treating E as E has only Ex hat, that is the only, it has only x axis and that is E. Okay. So, this electric field is not existing in Ey hat direction or Ez hat direction, it has only Ex hat direction electric field. And since I have written x as positive in this direction, whereas this is positive and this is negative. So, that is why you are writing it here as minus Ex hat. So, now doing all these, and if somebody is only looking at x component because there are other components will be gone. So, if one focuses on this, then they are left with only this term would be left with, because this is, there is no external force, this is gone, this is gone. So, one will left with this term and this term. So, now this term here one uses Poisson's equation once again and ended up with this. You remember the Poisson's equation? What did we do at that time? This was the Poisson's equation. Grad square phi is equal to minus rho El by epsilon. So, that means what we did here is grad square phi is equal to minus rho El by epsilon. So, rho El is given here as grad square phi into epsilon from that equation, Poisson's equation, and grad of phi is here as E. So, this is how this equation is changed using Poisson's equation, it came from here to there. So, then you write this entire thing under del z. So, this is a particular nomenclature one must make note of here, is that when we write del t v, that means del v del t we are talking about. Okay. When we write, let us say del z, when I write del square z v x, so that means we are talking about del square v x z del z square. So, like this. So, this is so we can write this as del z square into this quantity. So, now if we take, we have this as the boundary condition, that means at wall the velocity, wall means z equal to plus h by 2 and z equal to minus h by 2. So, at either of these the velocity would be 0. So, this is one boundary condition we have. So, if we apply these boundary conditions, if we take a solution of these, first of all del square this del z square is equal to 0. So, del z of this is equal to constant, right, and then this quantity would be then constant multiplied by z, like this. So, one can work with these and apply these boundary conditions, then this is the solution one ends up with. So, this is the solution one ends up with. So, with this solution, then in the last slide we have already derived this phi z as zeta into cos hyperbolic z by lambda d divided by cos hyperbolic h by 2 divided by lambda d. This is something which we have already established, that phi z. So, we are now just putting it here, and zeta we are taking outside. So, we are taking this zeta outside. So, this becomes, so zeta comes outside, and so this becomes the expression for V x z. So, here in green you can see this V x z is plotted. This is the velocity profile. If somebody plots these, one can see that this velocity profile, it develops within a very short distance from the wall, and then it remained practically flat. I mean, this is the trend of this 1 minus cos hyperbolic this thing, right. So, if you look at this profile, if somebody plots this, this is what they will end up with, and again near this wall there would be within a very short distance it turns to 0. And what is the velocity in most of these places in this entire cross section? That velocity is basically epsilon zeta divided by eta into E, this quantity. So, I mean, if somebody can afford to ignore this development of velocity near the wall, and if somebody is interested in what is the average over this entire cross section without considering this change within a very short distance near the wall, then one can simply work with these as the velocity. Okay, because most part of the cross section, this is the velocity that would be operating. What are the terms it has? It has epsa, which is permittivity, which comes from electrostatics. Okay. It has zeta. Zeta is that same zeta potential. We have a way to measure zeta potential experimentally, and zeta potential is a property that is this of the system. That means the wall material that you have chosen and the electrolyte that you have chosen. E is the electric field. That means how much voltage you applied. That means if the length of this channel is 1 centimeter and you have applied 10 kilovolt, then E would be this 10 kilovolt divided by the magnitude of E would be 10 kilovolt divided by 1 centimeter, because in unit of E is volt per centimeter. So, this is the E, and eta here is the viscosity. Eta is here is the viscosity. Okay. So, this is known as velocity electroosmotic. So, this is electroosmotic velocity, and if somebody does not bother much about this, they can very well say that if I apply a voltage gradient, then I can expect an electroosmotic velocity to develop within this fluid, and magnitude of this electroosmotic velocity is given by epsa zeta by eta into E. Eta is the viscosity of the fluid. That means sodium chloride solution, if you are working with, what is the viscosity of sodium chloride? If it is near, it is mostly aqueous solution, it would be the viscosity of water. Now, since I can apply a voltage and I could get away with I can produce a flow. So, now you can think of a situation where I have not applied a voltage, but now I have applied a pressure gradient. Here the pressure gradient is 0. Here the pressure gradient is 0 and the voltage is applied and I am seeing a fluid flow. So, now suppose I do not apply a voltage, but I apply a pressure gradient. So, I am having a flow against all these potential developing, charge electric double layer developing. So, then what would be the implication to the voltage in that case? So, that would be the next question immediately people will ask, right. So, here I must point out that electroosmotic flow develops by applying a voltage gradient. On the contrary, a streaming potential, which is given by the name ES, streaming potential across a porous medium develops when an electrolyte flows through a porous medium under steady applied pressure difference delta P. Okay. So, in this case now I am applying a delta P across the porous medium, and because of this delta P there is a flow taking place, but because of this electric double layer and this charge developing near the wall, charge building up near the wall, zeta potential and all these, there would be a streaming potential developing across the pore now, and that magnitude of the streaming potential is given by, in this case it is epsa zeta delta P divided by eta into Kb minus 2 Ks by R. Okay. I do not give the derivation here. I mean, I just added this slide because since we are talking about this zeta potential to understand why there is a dislodging or why there is a migration of particle. So, I thought that this is also an important information you must keep in mind here in this case. So, here epsa is the permittivity of the solution that is flowing through the porous medium, whose unit is Coulomb square Joule inverse meter inverse, and Kb in this case is specific bulk conductance of the liquid solution in ohm inverse meter inverse, specific bulk conductance of the liquid solution. Ks is the specific surface conductance of the pore structure in ohm inverse, and R is equal to pore radius in meter. So, the streaming potential is very much an important concept. I mean, when particularly when people are working with microfluidics, when one is working with a porous medium in a microfluidic sense. Suppose I mean, I can give you a small example quickly, that suppose there is in case of a microfluidics, let us say there is a porous medium and some fluid I do not know, say let us say I have a mixture and I know that I have a mixture here, out of that some fluid would be travelling through this porous medium. Which fluid is travelling? So, I have a way to measure these ES, the streaming potential. So, from these I can get some idea what fluid is flowing through this porous layer. For example, one is talking about a cell membrane through which there is some flow taking place. So, cell membrane, I mean to say biological cell membrane. So, one can measure the streaming potential, and from there one can think of going backward and see what was transporting through that membrane. Okay. What should have been streaming potential had this been the fluid with this bulk conductance, etc. So, this streaming potential is extremely important in from the concept of microfluidics. In fact, this electro-osmotic flow that I mentioned just now, this is also very important in the concept in the context of microfluidics, because there is a concept called electro-osmotic pump. Since this is known as electro-osmotic flow, so there is a concept called electro-osmotic pump. So, electro-osmotic pump operates on this principle that there is a channel, and I mean it is not a micro channel as such. They construct a porous medium, and with the understanding that inside porous medium such type of channel will develop, and such type of ion this electric double layer, etc., they will form. And so, if I apply a voltage across these, I will simply have a flow, okay, very precise flow. So, there is a channel filled with glass beads has been considered for making this electro-osmotic pump. This pump can deliver a flow, of course, but this flow would be very precise, and this pump will operate only by application of a voltage. So, only by application of a voltage this pump will operate, and I mean whatever voltage is applied, a very precise flow would be generated at the outlet. So, no moving parts, or no I mean what conventionally we see in a pump, for example, piston, impeller. So, those will be or even in a microfluidic sense, there would be piezo operated there would be other, I mean even if there is not an impeller, but a similar mechanism would be in place, but that needs huge amount of investment in terms of micro electromechanical systems. But here, by a simple channel filled with glass beads and by applying a voltage, one can create a pumping action where the fluid will flow. This is known as electro-osmotic pump, and for this a porous medium is used as this to create this kind of a channel. And so, this is electro-osmotic pump, and on the other hand it could be the other, if a porous medium, I mean say for example, a cell membrane where you see this is the streaming potential, then from that one can go backward and find out what is transmitting through these membrane. So, these are some of the microfluidic applications, and I thought I must mention this as part of this lecture, since I am discussing about these electro-osmotic flow, and since I am discussing about this zeta potential. So, essentially this zeta potential is, there will be an overlap of electric double layer which will cause the repulsion, and this fines will be then dislodged from the surface. So, what I will do in the next lecture is I will close this discussion on this why these fines get migrated, and then I will get into immediately what kind of conceptual models we have when it comes to these interception process. That means, I have a pathway through which some particles are flowing. So, what is exactly happening there, how the plugging takes place, and how we keep track of it. For example, are you supposed to write a continuity equation now on the particle itself, or what is it, how we characterize that, because essentially at the end of the day we are interested to know how pressure drop changes. So, if there is a plugging, pressure drop will increase. So, at what rate it will increase, can we predict this? So, that is something which we are heading to in the next lecture. So, that is all I have as far as today's as far as this lecture module is concerned, and thank you very much.